Okay, good. So the last thing on our notes, I believe, is the velocity squared frictional force. Is that the one? Friction proportional to v squared. Let's see what we have here. I think so, right? Pretty much. So we're still integrating Newton's law of motion in one dimension. So I can write it this way this time. dv dt equals f of x, v, and t. We've done a couple of examples. And what we're trying to do when we add something to the basic constant force, we get a much more complicated solution, something with different character. And when we let the frictional coefficient go to zero, then we regain our well-known free fall expressions or constant acceleration expressions. Okay, so I had I'm thinking this was more or less the last thing we had. So we were going to have the positive direction down. We had g minus b over mv squared. Okay. Now we're going to solve this one a little bit differently. We're going to work with the left side first. And look at, we're just going to use the chain rule. This is possible in one dimension. So this acceleration is equal to dv dx dt. Right? The little chain rule. And this dx dt is, of course, the velocity itself. So we have dv dt is equal to dv dx times v. And we're going to solve a couple of problems using this. And what we're now going to find is the dependence of the velocity on the position. And there's really a famous version of that that we're all familiar with. And so let's go ahead and try this. So our example is just free fall again, or constant acceleration. So we would have said m dv dt is equal to minus mg. So this time I'm putting the positive direction up again, okay, for whatever it's worth. Masses cancel for both sides, and we have v dv dx is equal to minus g. And now we're going to do separation of variables, which is this technique here. We have v dv equals minus g dx, and we integrate here from v0 to v. We can prime these v's here, and here from x0 to x. And the left side, the integral is, of course, just 1/2 v squared. Do a little prime again. V naught to v. And the right side, x minus x naught. Well, I already did the integral there. Okay. So this next step will show you something familiar. I'm going to multiply the 2 over to the right, and you'll see how I'll have v squared minus v naught squared. So on the left side, I have v squared minus v naught squared, and on the right side, I have minus 2g x minus x naught. So this is that third form of the free fall formulas that you guys remember from your physics 4A. V squared equals v naught squared. I'll just put your note. V squared equals v naught squared plus 2 acceleration x minus x naught. That's the one you guys probably remember out of your books, right? So yeah, we got that just by integration here. And we can do a couple of others as well. And And you'll notice the result is v of x. So we're not gonna get x of t directly out of that without some, special attempts. But yeah, we have v of x. In a little while, we're going to see those 1/2 v squareds with m be the kinetic energy and that kind of thing. Okay. I want to give a couple more examples of this. In particular, we can do this problem in that form. I'll probably assign that as a homework. Okay. Everybody see these steps? This is Newton's law, and but we're using this form right here. And we get this integration, which is a familiar result. And we're going to want to do something and get this as a limiting case now as well. So let's see which one we should go to. This one we're going to do as homework. Go ahead and rewrite this. Yeah. So here we go. This was our problem. Mass times acceleration is equal to mg minus, I used the letter b instead of k, dv squared. So that was that problem with the quadratic dependence. Remember, we solved the linear dependence. And we saw that the linear friction law would be for slow speeds, this one would be for high speeds. Okay. So we're going to go ahead and tackle this with m dv dx times d equals mg minus bv squared. We'll divide by m and separate variables. So m, and then we'll have dv times v divided by g minus v over m v squared is equal to dx. So that's the separation of variable step. You know, all put one variable on one side, another variable on the other. And integrate both sides. We can do x0 to x, v0 to v. Now remember, the only difference between this and what I just had on the board was this friction term. So when we finish integrating this thing up, if we take the appropriate limit, we should get back that other v squared result. Okay. But first we have to do this integration, which I'm going to put as a homework. This is a nice one. And I'll just give a few tips on this. So the homework problem is integrate this equation star here to obtain, I'll just say right from the get-go, we're going to get v squared as a function of x out of this. Then take the appropriate limit, and the appropriate limit is b goes to 0 to find that, v squared equals v0 squared. In this case, it's going to be plus 2g x minus x0, because we put the positive direction down. So yeah, we'll get that. Before that though, we're going to have something that looks a little different. So how do we do this integration? This one is really friendly. Precisely. If we do a u substitution, so if we let u equal v, v squared, du will be 2v dv, and the thing turns into a nice, well-behaved logarithm. Okay. So it won't be any problem on the integration. Then you can go back, then you can substitute u back in when you're done. You've got your v squared. And then you'll have to have a look at it. There's some exponentiation involved, wondering how the limit will give you this back again. Right, which we're confident that it should, because we just solved the case with b equals 0. So yeah, that's a good one. Let me give a couple other examples of how we use this technique. Put a little more commentary on this. So again, this was just so we have this here. This was fall with quadratic friction law, and that's for higher speeds. Just to tie together with what we had on Wednesday. Higher speed friction law. Okay. What do you guys think? That should all tie together nicely. The other one we had, I'll look it up. The linear friction law getting x of t. I think that was for next week's homework, right? The integration to that one. So all those problems will go together very nicely, and they are just reducing to constant acceleration. Now, another example of just integrating the equations of motion. This one's a little bit contrived, but it has good potential to interpret it. So the example here is we're going to have m dv dt is equal to minus, I'll just use the letter k again, v to the 1/2 power. So, first of all, what would we even be looking at? We're looking at a one-dimensional motion, and the force on it is purely velocity dependent. So we can imagine something sliding, and this is the velocity. This is the friction law. Something is sliding in the x-axis. You know, it's moving forward, and it's subject to a friction law in the opposite direction of motion. That would be the idea here. So yeah, let's go ahead and see how do we integrate this thing. We're going to use our method there again. So we're going to have v dv dx for the acceleration. We're going to divide by m both sides, v to the 1/2. And yeah, now we have to do separation of variables again. I'm getting the v's on one side, the x's on the other. You'll notice something. What's going to happen here is I'm going to have, when I divide by v to the 1/2, I'm going to be left with v to the 1/2 dv, and I'm going to have minus k over m dx. And we're going to integrate both sides. Again, a somewhat contrived friction law, but there's purpose here. So let's just work it and see what comes out. So, yeah, once again, you know, we were moving forward, but we had a friction law that's in the left opposite direction, positive x. So yeah, what do we get? If we integrate v to the 1/2 dv minus k over m dx, x naught to x, v naught to v, integration, variable b prime. Then we just have here 2/3 gonna go ahead and multiply both sides by 3/2, just to simplify that, and I'm going to get b to the 3/2 minus b0 to the 3/2 equals negative 3/2 k over m x minus x naught. Yeah, so that looks a little unusual. If we wanted b of x, we'd have to bring this thing over first. B naught 3/2 minus bk over 2m x minus x naught, and then we'd have to take it to what power? 2/3 power. But if we check our initial conditions now, so we want to interpret this thing. So at x equals x naught, that's when the action starts. This is a 0, b naught to the 3/2 to the 2/3. There's our b naught. Okay. B equals b naught. And what else is interesting about this problem? We could say, well, so this is the first thing. The other thing would be, how far does it travel, right? So we're pushing this thing, we give this thing a push, and it travels, and it's gonna come to a stop. So the interesting thing would be, how far does it travel? So, how far? So how far does it travel? There we take the left side, and it has come to a stop now, so b is equal to 0. And then we have this b naught to the 3/2 minus 3k over 2m x. Actually, the x minus x naught, we'll just say distance d, right? So at this point, it came to a stop. X minus x naught is the total distance traveled, distance d. And what we want to do as our final step is solve for d and interpret it and see if it makes any sense. Okay? Because we're trying to make sense of all these things. This is a perfect example. So solving for the distance traveled, we get b naught to the 3/2, put a 2 in there. In fact, let's go ahead and make this look better. So we'll have 2m b naught to the 3/2 divided by 3 times k. Good. So who wants to take a stab at explaining why this makes sense or why it doesn't make sense? So each of these parameters, we can argue, is sensibly located and makes physical sense. Remember, we pushed something against some frictional law and it came to a stop. Yeah.
I mean, okay, more mass makes the distance greater, which makes sense because it would have more inertia.
More inertia, right?
More velocity, it would just have more velocity to lose, so it would go farther.
Yep.
And greater frictional constant, it's smaller, so it's experiencing more friction and going slower.
Yeah,
faster.
and
So
what
it's
if
the,
k goes to 0? What about the distance?
infinite motion.
Which means, it never stops. Law of inertia. Basically, if k goes to 0, that's Newton Galileo law of inertia. So yeah, and this is the skill we want to have on interpreting formulas. That's why we don't like to plug numbers in for anything, unless there's a prize, because we can understand this thing: inertia, initial speed, frictional coefficient. So that's why I think these contrived examples are really nice, and I can make up a whole bunch of them and put one of them on the exam, right? Like we can do this as an exam type problem. I just have to choose a different power than you did. And there's actually another interesting thing here. All three of these were right, but you can say that this ratio here, M over K, is what's controlling it. The ratio of the mass to the frictional coefficient. Okay. But yeah, when we're talking about the free fall of a feather, we have the same thing with different powers, right? We have the mass, the frictional coefficient, and this should be involved as well. Good, so yeah, I like these examples here for that reason. You get used to thinking what the physics is and if it lines up, and here it does, okay? All three of those quantities. Good, so that is actually what we wanted to accomplish in this section. Next week, when we hand the homework back, we'll be able to review these and discuss them as well. Okay. But we now have a big set of these. We have these, for example, this homework of the one that I had up here before with the limiting case for that coefficient B. We have the limiting case for the integration of the linear law, the linear friction law. So we're ready to move into a different class of forces, namely the forces that depend on position. So I'm going to erase this. So once again, we have working in one dimension, degree of freedom. And we've looked at a few of these, right? We've looked at the explicit time-dependent one, we've looked at velocity-dependent forces. Now we want to do, so next, force is simply a function of position. And of course, these are the really important ones for a lot of things. What are some of our examples? And of course, we're going to cover these. Trivially, but still important, F equals mg can be counted among those, even though it doesn't have an explicit dependence, right? But the ones we're really after, 1/2 kx squared, because that'll be the whole discussion with oscillations. And also very important in 3 dimensions, but interesting in 1 dimension, minus k over x squared, because that'll be the inverse square law. Question?
Towards the second formula, shouldn't it be just kx?
Oh yeah, did I make that mistake last time too? Erase that. Yeah, I already jumped up to the potential energy, which is jumping the gun. It's actually minus kx, Hooke's law. Okay, I gave away the punchline on that one. Nonetheless, there's our collection of really important force laws in 3 dimensions as well as in 1 dimension. We can study it in 1 dimension. And of course, remember I had given the example of position and velocity with the Lorentz force, right? The electromagnetic one. We're going to come back to that one. But right now it's functions that are forces that are functions of position. Functions of position only. Yeah, immediately the next thing that one does here is define the potential energy. So forces that only depend on position can have a potential energy function. So I'm just going to write here, define potential energy U of x is equal to minus the integral of this force law from some arbitrary constant to x. So the argument of the potential energy is the upper boundary of this symbol here. And A is just some constant. So when you have a function like this, you also just have the fundamental theorem of calculus, and we can say du dx is equal to minus f of x. Right. The derivative of this construction here with the argument at the upper bound is the integrand evaluated at the upper bound. You guys remember the proof of this? Maybe we'll do that later. Everybody recognize this though as a fundamental theorem of calculus. Very important. We'll do the proof sometime. We'll do a recitation. It's a good one. But yeah, so we have that, and then we can just construct our consider one half mb squared plus u of x equals E. So there's a couple of ways to get there. I'm actually just jumping the gun and writing down the conservation of energy formula. We can also go ahead and erase this here. We can do this two different ways. Since we had Newton's law, maybe we'll put this one in first. This actually better shows where this comes from. So actually, before we consider this, let's just go ahead and remind it that we have m BDT equals f of x. Now we can multiply both sides. So I'm just multiplying both sides by the same thing, by velocity, and integrate both sides. T and then we get mv squared over 2 minus m v naught squared over 2. F of x dx. So that's where this comes from. Okay. But what I wanted to just make sure we see that. So keep that in your notes and leave some room around it. Because what I wanted to do was just take the time derivative of this expression here. So this would be a claim. I'm claiming that this equals constant. Right? This is your conservation of energy expression. I'm claiming that the kinetic plus potential is equal to a constant. And what I do is I take the time derivative of this and see if it equals 0. But the time derivative of this thing is going to be 1/2 m chain rule 2v dv also add a V. And this is left side, and this is du dx, which is minus F, right? Du dx is minus F. So mass times acceleration minus F equals 0. Okay. So that's the proof of the conservation of energy expression. This construction is actually where it comes from. Okay. And this is the form that you're never going to forget, right? You remembered it this whole time. Kinetic plus potential is constant. Okay. So that is a feature of a force that is purely a function of position. And this is in one dimension. When we do it in 3 dimensions, we're going to have to say a little bit more about the force, but it'll also be true. Okay. So equals 0, and write down here because mass times acceleration equals force. And when we do this with many degrees of freedom next semester, it will also be a very similar calculation. So yeah, this opens up a whole new set of possibilities when we have conservation of energy. We already just had it there a minute ago when I just did the constant force, the constant acceleration integration, right? When we had the half mv squared, but we had to express it in terms of potential energy. So let's look at that real quickly. Now we got time. This is good. Yeah. So that's how that comes into existence. You get the potential energy and these relations here. So now we're going to go back and look at everything under this aspect. In particular, potential energy examples. So we had F equals mg. For the first one, for the second one we had F equals minus kx. And for the third one, we had F equals minus k divided by x squared. So what do we get for the potential energies? And then we'll look at the conservation energy. So for this one, we have U equals minus integral a to x. Should I put the minus? I'm going to put the minus sign in here. Plus direction up. Okay. Minus negative mg dx. X minus mga. This, of course, is just a constant, and you guys are familiar with this. U equals mgx plus some arbitrary constant. That's the potential energy for free fall. So we have free fall. In fact, let's continue this example with what I just had up here. And this will touch base with our earlier calculation. So when we have this right here, or this one, we have 1/2 mv squared plus mg x equal to constant. We could say it's 1/2 mv naught squared plus mg. Well, we used a, so we'll use a naught, we'll use x naught. That's what our a is in this case. And what happens when we solve this? B squared equals b naught squared plus 2g x minus 2g x minus x naught. That brings us full circle, right? We've done this example 2, 3 different ways now. So that takes care of this one, want to at least get to that, we can do them all three. So what about this next one here? So for this next one, for number 2, we've got f equals minus kx. So now we have u equals negative integral a to x minus kx dx integration. We get integral kx dx. I don't have to do that. Okay, minus times minus is plus, so we get the k. And the integral of x dx is, 1/2 x squared. So we get 1/2 k x squared minus a squared. This is just a constant, and we typically leave that equal to 0. Let that equal to 0, so let a equal 0, then we have u of x 1/2 k x squared. I think I wrote down a little prematurely before. Potential energy for the linear, for Hooke's law. The linear restoring force, that's what we would call that. Linear restoring force. And this one's going to be really interesting, of course, when we study gravity and towards the end of the semester, Kepler problems, central force problems. And of course, this one will be in 3 dimensions, then 2. But we're going to see there's actually a really interesting application in 1 dimension on this one as well. So definitely worth talking about the inverse square law in just 1 dimension. So good. Okay if I erase these here? Yeah, so let's have a look at this next one. So here, for the inverse square law, potential will be minus integral negative k over x squared dx integration constant a to x. So we're going to get here, we've got that inverse power. We're going to have minus k over x. X. And the convention here is take a out to infinity. You're going to have a 1 over a. You take a out to infinity, then that's 0. So a, let a go to infinity. Strictly speaking, doesn't have to, but that's a useful convention. And we just end up with minus k over x for the potential for the inverse square law. So now we have u of x minus k over x. And you can immediately graph this thing. And for x greater than 0, which is what we're interested in on this one, it looks like this. We're dealing with this one in math methods, but we need it here too. So the interesting question that we can leave off with here, what's the relation of this and the one we just talked about for free fall? How are u of x equal minus k over x and u of x equals mgx, how are they related? Double question mark. Anybody know that? This is gravity, right? This is Newtonian gravity, and this is also gravity. They can't contradict each other, yet they look very different from each other. tackle that. And, it's an interesting problem. This one, you can say this one here segues right into that one, if you look at it at the proper scale. So we're gonna do both of these, but, that's enough for today. Yeah. Any questions on these? So anything I assigned for homework today, of course, is it next week. And the other ones we'll try to get in by this afternoon.